Welcome to my YouTube channel. I am Dr. Arvind Joshi. As you know that I have explained about the graphical representation of linear discriminant analysis in my previous video, and it was a very simple one. Now, though the mathematical part is very much typical and it requires a lot of linear algebra, but what I did over here in my presentation, you will see that I have given the basics of linear algebra. And by knowing this basics of linear algebra, you will easily solve the problem of linear discriminant analysis, and you will easily understand the algorithm of linear discriminant analysis. We have this equation y is equal to w0 x0 plus w1 x1 plus w2 x2 plus and so on wn xn. So in terms of matrix, we can put these things. This x, capital X is equal to, this is a matrix of x0, x1, xn elements, or say features, right? And here we have w is equal to w0, w1 and so on wn. These are the slopes of different slopes, w0 x1, w1 xn, w2 x2, and these are the slopes. Now, the transverse part of this matrix W is denoted as WT. This is equal to W0, W1 and so on like this Wn. While this, if you will write this together X and W in a matrix form, it will come out to be W0, W1 and so on Wn, X0, X1 like this, right? This W0 is called the transverse part. So the equation will become y is equal to WTX. So this is the matrix equation in linear algebra, right? So here WT is a matrix symbol. T denotes that it is a transverse of W matrix. So WT denotes the direction of y as it is the slope of line. So y is matrix space and X is also a matrix space. So we have to create a matrix space in LDA. We have this X space and we have to reduce the, features or the dimensions by the help of set of rules or the algorithm of LDA. Now, for X matrix space, see here, for X matrix space, projection is Y space. This is the Y space, this is the X space, and the projection of it is here in the Y space. So the relation between these two spaces, X and Y space, is Y is equal to W transverse X. This you know well. This is the relation. Okay. And Y is a subspace. This is a dimensity reduction part of it. We have reduced the dimensions of X space and have imposed them or projected them in the Y subspace. We have created this new subspace. The relation between this subspace and X space is Y is equal to W transverse X. Now coming over here, there is some kind of terminology you should have to know, that we have two classes, C1 and C2, inside space X. As you are seeing, these are the two classes, C1, and this is C1, this is C2. This is space X. We have two classes, right? And mu1 and mu2 are called as the mean of classes C1 and C2 respectively. These are the mean of these classes, mu1 and mu, right? And the projection of this mu2 mean is the mu2 projected mean, and this is mu1 projected mean in subspace Y, right? So if projected mu1 and projected mu2, these are the projected mean in subspace Y of classes C1 and C2. Now, coming over the actual thing, linear discriminant analysis. Now, let us assume a d-dimensional data frame. I am denoting it by capital X. Okay. So it has d dimensions, x1, x2, so on to xd. So like this. And I have depicted this data frame, or say feature space or a data frame. It is like this. These rows are called as the sample 0, sample 1 to sample n, right? And we have the columns x1, x2, x3 to xd. Okay, so this is our data frame, and this data frame is in X space. Okay, now what we are doing, let us say that we are dividing this data frame, or say data of the X space, into two groups, C1 and C2. Out of the given feature space X of dimension D, let N1 belongs to class C1, right? And N2 belongs to class C2. So what is our aim for the LDA? The rule is this: maximize the separability of class or classes, that is between class variance. The class variance or the separability between class should be maximum, as our aim is to develop a class or group separability, maximum class or group separability, right? So for matrix space or feature space X, let C1 is the C1 class has mean mu1, as I have told you earlier, and C2 class has mean mu2. Now, for matrix subspace Y or projected space, let projected mean mu1 for C1 class and mu2 is the projected mean for C2 class. Now, according to the algorithm of LDA, we have, what is our objective? Our objective is to find the distance between the projected means, that is mu1 and mu2. So our objective function is JW is equal to mu1 minus projected mu1 minus projected mu2. Now, some definitions. Scatter matrix. If S1 and S2 are the measure of the scatter in multivariate feature space X for class C1 and C2 respectively, then S1 is equal to X minus mu1 into X minus mu1 transpose. Like this, S2. Both are the measure of the scatter in class C1 and C2. It is measuring the scatter within the class. So this is S1 and S2, right? Similarly, now the total scattering, therefore scatter matrix within class C1 and C2, if we will sum it up, so SW is equal to S1 plus S2. So this will be the equation if you are putting the value of S1 from here, and the value of S2 is this. Okay, this is our equation number 2, right? Then another definition, similarly for subspace Y, the measure of scatter for two classes C1 and C2, as we have taken the measure of scatter here S1 and S2, here we are taking as the projection part of it. This is the sign of projection. Projection of S1 square is equal to, since Y belongs to class C1, because we are taking it Y, this we are taking in Y subspace. Okay. So this is capital Y minus mu1, projected mu1 whole square, and similarly this S2 square. Now, adding these two scatter matrix, S1 square plus S2 square projected, it comes out to be Y minus mu1 whole square, Y minus mu2 whole square. And since we know that y is equal to W transpose X. So, and mu1 is equal to mu1 transpose W, and mu2 is equal to mu2 transpose is equal to mu2 transpose W. This, for this you have to see this. See here, this is what I have done. Mu1 is equal to 1 upon n1. This, it mu1, projected mu1 comes out to be W transpose mu1, and projected mu2 comes out to be W transpose mu2. Now coming over here, S1 square plus S2 square. Therefore, on putting the above values, where in this case, Y, in place of Y, I am putting W transpose X, and in place of mu, I am putting mu into W transpose. Okay. So the equation comes out to be like this. Okay. For the calculation purpose, I have written it in short. This is W transpose W. If you will put the value, it will come out to be X minus mu1 into X minus mu1 transpose. And here for class C2, X minus mu2 into X minus mu2 transpose. And this is equation 2. See, this is equation number 2. Okay, this much, SW. SW is called the scatter measure within class, right? So I am giving it to value SW. Okay, so this is the value of SW. This part is a value of SW, this part. Okay, so S1 square, projected S1 square, or the scatter, sum of the projected scatter is equal to W transpose W SW. So SW is the scatter measure within class. Now it is clear. And I have given you some kind of calculation over here. As you will put the value of Y as WTX here, and mu1 W transpose over here, it will be a whole square, and you can calculate it by this method. This is the method. X minus mu1 whole square WT square. This is WT X minus mu1. This is WT, divided into two parts. Then write it in transpose way. And if you will transpose it, this WT will become W. Okay. So WT, so W transpose into W is equal to X minus mu1 into X minus mu1 transpose, right? So the value comes out to be in equation 3 as sum of the scatter of the projected scatter is S1 square plus projected S2 square is equal to W transpose W SW. This is our equation number 3. So now, another thing which I am going to calculate over here for our mathematical concept, this is the difference between projected means. We have to find it out. So this is the difference square, whole square of the projected means. So this comes out to be, because you know that mu1 is equal to W transpose mu1, and mu2, projected mu2 is equal to W transpose mu2, right? So when you will solve it out, see here, you will get, after calculation, you are getting under bracket mu1 minus mu2 into mu1 minus mu2 transpose, right? The calculation is same as I have written it in detail. Okay. So this mu1 minus mu2 into mu1 minus mu2 transpose, you will say it SB. SB is scatter between class variance, or say SB is between class variance. SB is a between class variance. So SB is mu1 minus mu2 into mu1 minus mu2 transpose, right? So we can say that this part mu1, projected mu1 minus projected mu2 whole square, it comes out to be in the form of this equation number 4 as W transpose WSB, right? So now we have the objective function in the form of equation number 1. We have the objective function to find the distance between the projected means. Now, by the help of this scatter matrix and the difference between the projected means, we will normalize this function, and the normalized function will be this. Okay. So this is JW is equal to mu1 square minus mu2 square whole square upon S1 square plus S2 square. Mu1, projected mu1 minus projected mu2 whole square is equal to S1 square plus S2 square. So this is JW. I am normalizing it, and this is called the normalization of this function JW. It is a very important function. And now what we will do? We will replace this quantity by this equation number 4. See, this is the equation number 4. So we will replace it by WT, W transpose SBW, and this quantity projected scattering S1 square plus S2 square by this quantity W transpose W SW. So see here this. So the equation comes out to be JW is equal to WT SBW. This whole is a matrix, and this is also a matrix. So do not cross it W by W and like this. This is a matrix operation we will do here, right? So this is the matrix equation. And now what we have to do, we have to find the optimal direction of the projection Y. Optimal direction. So what we will do? Now we will differentiate this cost function JW, or say objective function JW, with respect to this W, that is direction, that is slope. It will tell us the direction of the subspace Y. So by simple differentiation in this way, see, del J upon del W is equal to del W, W transpose SVW upon W transpose SWW. We will get an optimal directional matrix. W is equal to SW inverse mu1 minus mu2. This mu1 minus mu2, this direction W proportional to mu1 minus mu2, this should be maximum part of it. And this is the algorithm of LDA. And this SW minus 1, this is the inverse matrix for scatter within the class, while this mu1 minus mu2 is the difference of mean in between. This is the difference in between the feature space X in between the class X. So this is the algorithm of LDA. It is not very tough if you will go through all these details, minute details which I have given, and each and every equation I have put up before you. They all have made easy by the help of simple equation and simple class 10th linear algebra and class 12th matrix I have taken, right? So this is the algorithm part. If you liked our video, please don't forget to like, share, comment, and subscribe. Thank you very much.